Hello and welcome to another lecture for my class PSYC 770 Psychological Testing and Assessment. As usual, at least so far in this series of lectures, I'm beginning with a comic from the excellent series xkcd.com, and it's appropriate here, I think, because we'll be talking, or I'll be talking in this lecture about how we interpret test scores and how we communicate information about the constructs that these test scores hopefully represent. So like I said, today's lecture is called Interpreting Test Scores. Once again, not a particularly inspired title, but one that I think more or less fits with what I want to talk about today. I'll begin by talking about raw data, the actual numbers that result when we score up a particular test taker's responses on a particular test, and I'll ask the question, what does raw data mean? What do we do with it? I'll talk about this idea of relating individual scores, individual pieces of raw data, to the populations that those data supposedly come from. And in so doing, in making that connection between the individual test taker and the broader population, I'll talk a little bit about sample variation, error, and bias. I'll move on and talk a little bit about some essential statistical concepts. This will really be a review for, I think, almost all people who are taking this class, and probably a lot of people who are watching this video. Basically descriptive statistics for frequency distributions, describing parameter estimates for shape, central tendency, dispersion, and so on. And finally, I'll finish the lecture by talking a little bit about how we can transform raw data to make it easier to interpret, easier to communicate, easier to describe, and so on. So let's begin. Raw scores, raw data. What do they mean? Well, as I'm sure you can imagine, a raw test score by itself is almost always meaningless, or pretty close to meaningless. And you could imagine that you've come into my office, I've administered some test of, let's say, intelligence, and I tell you your score on this test is 42. Almost immediately you're going to be asking yourself, or probably better yet asking me, where does 42 lie with respect to most other people who take the test? Is that an average score? Is that above average score? Is that below average score? Or you might be asking, what does 42 mean for me? Does it mean that having earned a score of 42, I get access to certain sorts of classes or resources, or I get referred for certain sorts of treatment or support or whatever else? Either way, you're asking questions, which are good questions, which have to do with putting that raw score into some sort of a context so it can be interpreted. Now, as I've discussed in previous lectures, most tests, at least most of the tests that we're going to talk about in this class, are norm-referenced tests, meaning that we interpret raw data with respect to some sort of a distribution of scores from a standardization sample that, as we'll discuss in later slides, hopefully is representative of some broader population that the individual is part of. So if I say, well, your score 42 is average or typical for people who are of your age or have your level of education, I've put your score in a context with respect to, or by referencing, a norm, an average from a sample that's hopefully representative of an average of the population that that sample is drawn from. I've also mentioned in previous lectures that some tests are interpreted, or the scores and results of some tests are interpreted with respect to one or more criteria. So often in the case of educational testing, we might say, well, if someone's score exceeds a certain level, then he or she can place out of a class, or if it falls below a certain level, he or she is referred for supplemental instruction or support from a testing center or whatever else. Those are examples of using criterion-based decisions around a test result. They're, again, probably more common in educational settings than in clinical psychology settings, but you could think of at least a few examples, I suppose, in clinical psychology. There are a number of tests which have cut scores in them for determining whether or not someone meets a diagnostic or is likely to be part of a diagnostic category. That's a somewhat criterion referenced test interpretation. But anyway, whether it's norm referenced or criterion referenced, the important idea is that test scores need to be put into context. So again, just to repeat myself, the important point, or an important point here, is that test scores need to be put into a context, either by making some sort of reference or connection between the score and some set of norms, or between the score and some set of criteria. That's an important point, and we really need to recognize that. It's also important to recognize or to acknowledge that people often miss this point. Well-intentioned, well-educated people can often get this wrong and can interpret test results without thinking very carefully about the connections that they're trying to make between test scores and norms, or test scores and criteria. This is probably especially true in the case of tests which measure value-laden constructs like intelligence or some features of personality or features of mental illness. Of course, many of the things that we're going to be talking about in this class are, to a greater or lesser extent, value-laden. People really care and worry about what their scores on your test will be. And so it's easy, if you give someone a test result, like your score is 42 on this test, for that person to immediately start worrying and thinking ahead and getting beyond the point of asking those important questions about context. And it's probably true to say, or fair to say, that this is more so the case for people who are non-psychologists, and thus part of our responsibility as psychologists is to be very careful and clear in our language as we describe test results and our interpretation of those test results to other people. But as we saw in the last lecture, I think psychology itself can't claim to have avoided this problem. Historically, there have been plenty of examples of times where successful, intelligent psychologists have misinterpreted tests of important value-laden constructs because they weren't careful about how they were connecting individual test scores to either norms or criteria. To pick one quick and rather easy example, in his early use of the his early use of the Binet-Simon scale, Goddard at the Vineland School simply referred or compared the test scores of his mentally disabled and developmentally disabled clients to the original French norms, which is probably not an appropriate comparison to make unless you argue that those folks he was testing were part of this population that Binet and Simon had gathered data on decades earlier in France. So an example of some pretty basic mistakes being made by someone who probably should have known better, or at least we can look back from the perspective of history and say, aha, we now know better than that, or at least we should know better than that. So I've been saying these words and kind of dancing around this point already, but really what we're trying to do, at least with norm reference test, is make a connection between individuals, or an individual, and a population. And to do that, we start, of course, with an individual score. So the data from one case, the person's full-scale IQ score, or their level of neuroticism on the NEO-PI, or their level of some element of psychopathology on the MMPI, or whatever. We have that score based on the results of the test that we administered to this one client, or this one student, or this one patient, or whatever. Now what we don't have is the data from the population. That is, all the possible cases that we could possibly measure using our instrument. So we can't know precisely where our one individual lies with respect to all other possible individuals who could be tested by us, because of course that's practically speaking impossible, for us to gather all that data. But what we can do is we can describe what this population, or this distribution of values in the population, probably looks like. Statisticians refer to features of a population distribution as parameters, in the sense that these are measurements which can't be made precisely, but rather can be estimated from samples of data. And that's kind of what we're getting at right here. So what we can have, or what we should have if we're trying to interpret a test with respect to norms, is some sort of sample of data, data from a group of cases, ideally published in the test manual. So if you open up the manual for the Beck Depression Inventory or the Wechsler Adult Intelligence Scale or any other major well-developed test, you'll find information about the large and hopefully rather representative sample of people who were tested using this instrument, so as to get a sense of what the norms are for that sample. Those norms hopefully being technically statistics for that sample, hopefully being reflective of the parameters of the population that the sample was drawn from. Now, an important point to acknowledge here is that we have, or the test manufacturers and publishers have given us in their test manual one set of norms, means, standard deviations, etc., from a sample of people drawn from a population. But we know that if we had another sample from that same population, those values would be different, maybe slightly different, maybe a lot different. We have norms based on several hundred people on the Beck Depression Inventory. Let's say, what if we gathered a new set of several hundred people and administered the Beck Depression Inventory to all of them, and we looked at the means and standard deviations and whatnot in that new data set? We'd expect them to be somewhat different than those from the original data set. Statisticians and methodologists call this sampling variation or sampling error. This is just something that's observed really throughout science. If you make measurements of groups of cases and then you draw new groups of cases, anything that you're measuring or computing is going to be slightly different in that new sample as compared to the old sample. And indeed, you could make a distribution of a particular measurement or a particular statistic by repeatedly sampling a population and plotting the mean for each sample, let's say, or the variance for each sample, or whatever else. This is just something that statisticians and methodologists have been aware of for quite a while now. And to focus a little bit more, we can say that sampling variation or sampling error comes in really two types or two flavors. The first is unsystematic variation or error. By the way, I'm using variation and error interchangeably, and there's certainly a history of statistics using those two words somewhat interchangeably. Anyway, one form of sampling variation is unsystematic, that is just random error that is, or variation that can't be easily attributed to any known variable or factor. Then there's also systematic variation or systematic sampling error. This is non-random and in some cases can reflect bias in our sample with respect to the population it's drawn from. And I want to focus on that idea of bias for a couple slides right now. Now, clearly, bias is a word that we use in our common language and can have all sorts of meanings, especially with respect to things like bias against people of particular genders or sexual orientations or ethnicities or so on. What scientists and methodologists, statisticians, etc. usually mean when they talk about bias is an idea of a measurement that systematically misrepresents the thing that it's supposed to measure. So you could imagine that I have a measure of intelligence, or I have a measure of some feature of personality, or I have a measure of frequency of use of alcoholic beverages, or whatever. And if my measurement tends to mismeasure that thing, then that's an example by definition of bias. Well, why does this happen? Well, as we've said before, scientists can't study entire populations, at least not in the sense of gathering data on all elements or all cases in entire populations. They can only study samples from that population, and the samples can be representative of the population, but they might also not be representative of the population. Again, that idea of sampling variation or sampling error. So in an attempt to represent this pictographically, let's imagine that all these dots here on the screen represent all the cases in a population that you wish to study. Let's say it's all people between the ages of 18 and 25, sort of the late high school to college age to early adulthood years, which for all sorts of reasons we often are interested in studying. Now, some of the people in that population, you can think of as like a subpopulation within the broader population, are college students, and some of them are not college students. Now, you can't study the whole population, there's just too many people. But let's imagine you draw a sample, and whether you realize it or not, your sample overrepresents or is disproportionately populated by college students as compared to non-college students. If you spent any amount of time doing research in a psychology department, as of course I think pretty much all the people watching this video have, you know that this is a pretty common thing to happen. You're trying to develop a new measure or for your research or for your testing or whatever else, and so you gather data from the people around you who, surprise, surprise, tend to be mostly college students like yourself. Well, what if college students differ from non-college students? And of course they do. We know that people who are in college have higher levels of education than people not in college, and that's almost true by definition. They tend to have higher levels of drug use and alcohol use. They tend to have lower levels of mental illness, not because being in college makes you not mentally ill, but probably more because being mentally ill makes it hard to stay in college. People in college tend to have somewhat lower levels of religiosity than people not in college, and so on and so on. So to the extent that you develop norms based on that sample and mistakenly think that those norms are representative of the population you're attempting to study, i.e. all people from 18 to 25, you may have introduced some bias into the way your test gets interpreted. Let's imagine, to draw back to that previous kind of example I gave, that I administer a test to you and I say your score on this test is 42, and you ask, well, is that high or low? And I say, well, it's about average. And you think, okay, well, that's good. And maybe what I'm communicating to you is that your score is average for people in your age range, but maybe whether I realize it or you realize it or not, that average that I'm referring to is an average drawn from a biased or sample of the population. So just to kind of be clear about this, what our goal is we're trying, at least in norm reference testing, to interpret test scores with respect to sample data that's representative of the population that we're supposedly trying to study or test. And the important point here is that these test scores, again, as I've said, need to be put into a context. They need to be put into relationship with a population distribution, which is estimated from a sample distribution. Where you lie with respect to the average in the population, we're kind of guessing at based on where you lie with respect to the average or mean within the sample. But if the sample is not representative of the population, then we might have a problem with bias, or misinterpretation would be another way of describing it, of your test results. Okay, so hopefully that's fairly straightforward. If not, as always, of course, try to ask me questions if you're in the class, or if not, post comments on YouTube, and I'll do my best to answer them. But with that all in mind, let's move on to the next section of the lecture. This is just called Essential Statistical Concepts. Don't worry, it's not nearly as complicated as this image on the screen would probably lead you to believe. Instead, what this next section of the lecture will cover is basically descriptive statistics, or stuff you've encountered probably in other classes under the title descriptive statistics. If you have data, in this case data from a sample drawn from a population, you're probably asking, or you would probably ask, what's the shape of this data? What's it look like? Well, how can we describe the shape of the distribution of values we have, or where the center of that distribution is, or how dispersed that distribution is, and so on and so on. And again, as you probably learned in other classes, and thus this is a bit of a review, one thing you could do is make a frequency table for that distribution. You could count up scores within particular bins or ranges and just create a table to tally them all up. Those bins ideally or often are equally sized, although they don't always have to be. Here in this little image on the bottom right of the screen, you can see scores on an IQ test from a large sample of people, and you can see that there are some folks who fall below 85, some more folks who fall in the 85 to 94 range, a lot of folks who fall in the 95 to 104 range, and so on and so on. And if you kind of squint at those numbers, you can get the sense that they represent kind of a slightly mound-shaped or maybe even bell-shaped curve if you were to plot them. And indeed, if you did plot them, you would have made a histogram, a bar chart that represents that frequency table or that frequency distribution. So here we could see not exactly the same numbers, but a similar idea in this little image. And if we want to be really fussy about it, we could say, well, you can make a bar chart, or you can make what's called a frequency polygon. That would be just if you, rather than using bars, made discrete dots and then connect the dots with them. Same idea, just trying to pictographically represent a distribution of the frequencies of different values for whatever your test is. Now here's part of the lecture where you can practice with this stuff. If you're watching this lecture and through my class and you're watching it through Blackboard, you can navigate around Blackboard and find easily a little data set to play along with. If not, if you're just watching this on YouTube, I'm not sure if I can attach a file. I'll see if I can. But anyway, let's just acknowledge or submit that I have a new anxiety measure that I've developed. Let's imagine, really it's just fake data I've made up. This is a pretty simple measure of symptoms. It's just 20 yes/no items, and the score for the instrument is made by totaling up the number of yeses. Higher numbers of yeses, of course, indicate higher levels of anxiety symptoms, lower numbers, lower levels of anxiety symptoms. What you need to do now, or what I encourage you to do, is create a frequency distribution, a frequency table, and a histogram for this data. Well, okay, hopefully you've done that right now. I'm coughing a little bit because I've caught a cold from my children. You now have a way of representing in numbers and in graphical or pictographic form a distribution of data. That's awesome. You can now begin to describe what that shape looks like, what the shape of that distribution looks like. And one feature of that distribution is its symmetry, whether it is evenly balanced left side to right side, or whether it tends to tail off in one direction or the other. And again, you've probably encountered this in other classes, but by way of a quick review, that quality of non-symmetry or directional non-symmetry is referred to as skew. Positive skew is a situation in which scores tend to pile up on the low end of the distribution and tail off to the high end. Negative skew is a situation in which scores tend to pile up on the high end of the distribution and tail off towards the low end. So just to get a sense of what that might look like pictographically, you can see positive and negative skew right there. We can also describe the shape of the distribution in terms of how peaked or how kind of mounded it is. And this is a little bit harder to describe in words, although I think once you kind of get it, it makes sense. It's a term called kurtosis. Kurtosis can occur in two ways. We can have positive kurtosis or leptokurtosis. This is a situation in which there are relatively larger numbers of extreme cases, very high values and very low values, than we would expect in a normal distribution, as we'll see in future slides. Negative kurtosis or platykurtosis is a situation of thinner tails or lighter tails, where we have relatively fewer cases at the extreme. Again, this is a little bit difficult to describe in words. It's probably easier to view here. This is a nice image you can see here of different curves that all have the same center, so none of them are skewed. They're all perfectly symmetrical. You can see in the heavy black line a normal curve, a bell-shaped curve, and we'll talk about this in future slides, but you're certainly familiar with this if you're taking this class. And you can see a situation of varying kurtosis from extreme positive kurtosis in the orange and red, where there's a kind of a very tall peak in the middle, and although this is kind of less obvious, they're relatively higher tails on the ends than in the normal curve. So if you kind of really squint, you can see that the orange and red at the high end or low end are higher than the black line representing the normal curve. That's extreme positive kurtosis, a leptokurtic distribution. There's a piling up of cases in the middle and a relatively sort of higher piling up on the extreme ends, positive and negative. Negative kurtosis we can see here in the blue curve, or maybe even more extreme in the purple curve. That's kind of a uniform distribution, so maybe ignore that temporarily. But look at that blue curve, or the kind of the light blue curve. Those are cases where there's a piling up in the middle, but the tails on either end are relatively lower than the normal curve. So if you squint at, it's not, you don't really need to even squint, if you look at either of the blue shades, you can see that at the high end and the low end, there are lower frequencies of values for those curves than there are in the normal curve, the black curve. So this kind of mound-like shape in the middle, and a kind of thin, or even in the case of the dark blue, non-existent tails at the extremes. So time for more practice. If you're taking this class, look at the data set. You should already know how to do this based on other classes you've probably taken from me, but try to describe the shape of the distribution. Describe it in words now that you've made that histogram, but then also describe it numerically. Try to compute the skew and kurtosis for this distribution. So again, once you've got a distribution of data, in this case data from a sample drawn from a population, one thing you can do is just create a representation of that distribution pictographically or in table form. You can describe its shape in terms of its directional asymmetry or its symmetry, and in terms of its kind of thinness or thickness of its tails, skew and kurtosis respectively, of course. You can also describe where the center of that distribution is, like where are most of the values piling up. And to do this, of course, we have some familiar calculations like the mean. The sum of scores divided by the number of scores, or put more simply, an unweighted average. Now we all know what an average is, and we all know, I think, that in many cases of data, the average is going to reflect about where most of the cases in the data set are. Certainly if you have a large number of people taking a class and you all get your test scores back, one of the first questions that any student asks is, what was the class average? Where were kind of most of the scores for the class tending to be? And am I much ahead of that or above that level, or am I below that level? Of course, another way to describe the center of the distribution is just to rank or order all the scores by magnitude from the very lowest to the very highest, and pick the value that lies at the middle of that set of ranks. This is the 50th percentile. It's the median. It's the middle point that evenly divides the distribution into an equal number of cases on the high end and on the low end, and that also gives us a sense of where the middle of the distribution is. And of course, if there are an even number of cases, what we might do is just pick an average of the two middlemost lying cases and call that our median. So again, like I just said. And finally, we have the mode. This is, again, something you're certainly familiar with from other classes. This is just the most frequently occurring value. So in the case of a histogram, it's the highest bar. That's the most frequently occurring value in the distribution. It's the most typical score that we see. All right, more practice. So go ahead and with your data set, compute the mean, the median, and the mode. So as you do this, as you describe where the center of the distribution of values is, you become aware, hopefully, of extreme values that are very far away from that center. These are, of course, outliers. And in a sense, we can think of them as distorting the shape of the distribution. So here's a distribution that looks, I don't know, let's be generous and say it looks kind of bell-shaped. It certainly has that familiar mound shape, at least. And you can see that there are some high values, though, on the upper end. There's actually some positive skew to this distribution. It's asymmetrical, and asymmetrical in the sense that there's some extreme high values. What's interesting, among other features of this distribution, is the fact that those high values distort the estimate of the center of that distribution. The mean and the median should be exactly the same values if the data was perfectly symmetrical in distribution, but the fact that there are some high values drags the mean away from the median. You can see here the mean is slightly higher than the median. That wouldn't be the case if the distribution was perfectly symmetrical. See, outliers are interesting to us because, well, for all sorts of reasons, really, but some of the reasons are that they distort distributions, and they distort our estimates of the central tendency, or the center of a distribution. The mean, as you know, I'm sure from other classes, is exquisitely sensitive to outliers. And one important lesson to take from that, or important idea to take from that, is if you had a distribution of values that did contain outliers, you might know, or you might suspect, the mean as being a not particularly useful way of estimating the center of the population mean, because that mean in the sample is being pulled off by those outliers. The median is somewhat less sensitive to outliers, and the mode is even less sensitive. So again, to repeat that point that I made just a second ago, when data are skewed, when there are outliers, the mean becomes problematic as a way of describing where the center of the data is in that sample distribution, and as a way of estimating where the center of the data is in the population. Those outliers throw things off. That skew can throw things off, and in those situations it's sometimes preferable to use a median or a mode as the way of describing roughly where the center of the distribution is. Another opportunity to practice. We as teachers are encouraged to do this active learning thing, to give you guys problems to work through on your own. Try to identify outliers in your data set. Are there any outliers there? And how can you decide whether a particular value is an outlier? Clearly, if a value is much, much larger than the others, it seems like a likely candidate for being an outlier, or indeed if it's much, much lower. But how do you make a decision as to whether a particular data point, a particular case, is truly an outlier or not? So work on that, think about that. Moving on, we've described, or in talking about sample data and using this kind of review of descriptive statistics, we've said, well, you can describe the overall shape of a distribution, you can describe the central tendency of that distribution, you can also describe the dispersion of the distribution. How spread out is it? And the most obvious way to do this is to talk about the range, which is just simply the smallest value subtracted from the largest value. And as a quick note, it's worth acknowledging, of course, that outlying values on either end really throw off the range. So the range is a pretty good way of describing how spread out the data is, unless you have one or more really high values or really, really low values, in which case the range looks much bigger than, in a sense, it should. It gives less information, or less accurate picture of the dispersion of that distribution. Recognizing this, we sometimes compute, instead of range, quartiles in the data. So quartiles are just a way of dividing up the data into four equally populated chunks. So the first thing we would do is we'd split the data at the median, dividing into a high half and a low half, and then we'd split each of those halves to yield 4 total groups. And the first quartile is the median of the lower half, the second quartile is the median, the original median, and the third quartile, that third cut, is the median of the upper half. So we've got sort of 3 cuts producing 4 groups, and we can talk about these quartile cut points, and we can compute, if we want, the interquartile range, the range between the high quartile, the third quartile, and the first quartile. And that'll give us a sense of a range across most of the data, and it's less affected by skew or by outliers than the raw, kind of unadorned, full range of the data. So if you're having a difficulty picturing this, here is a distribution of values, and you can see different ways of kind of describing portions of that distribution. At the very top, there's a box plot lying on its side, and you can see in that box plot Q1 representing the first quartile cut. Unlabeled is Q2, that's the median, and then Q3, and the interquartile range is just that range between the high third quartile and the low first quartile. It's also interesting to note, of course, that in normally distributed data, that's going to be 50% of the cases. So you could think about the interquartile range as describing the range across half of the data, assuming or knowing in advance, if you did, that that data was normally distributed. Now, there are other ways of describing the dispersion of a data set, in this case a sample from a population, and one that you're probably familiar with is the variance. So this is just the dispersion of squared scores, or the average squared deviation from the mean. So we take each value, each person's score on our test, we subtract from it the mean for all people, we square it so that we can get rid of negatives and we don't sum to 0. Then we add up all of those squared differences and divide by the number of cases minus 1 if we're trying to estimate the population variance, not minus 1 if we're just looking at the sample variance as such. And that gives us a sense of like the average amount that individual cases differ from the mean of all cases. If we want, we can square root that value and take the positive square root of it. That's of course the standard deviation. It's the average of the deviations from the means. And what's nice about this is it's in the same scale as our original test measure. So if you said the variance of a particular measure is some value, that value is actually in terms of squared units of the original test, but the standard deviation is in the same units as the original test, which makes it a little bit easier to think about. So if I said, well, the mean for this test is, this measure is 100 and the standard deviation is 15, those 15 are 15 points just like the points that you would score up in the test itself. Okay, time for more practice. Go ahead and compute the range, the interquartile range, the variance, and the standard deviation for this practice data set on my new measure. Okay, moving on, let's talk a little bit about the normal distribution. Now, you've certainly encountered the normal distribution in other classes before, and I've mentioned it already in this lecture a couple times, but it's an important concept and it deserves a little bit of additional attention. We can begin with the observation that most data for most things that we measure in psychology, and indeed in most of the sciences, tend to vary. So if you gathered a large number of measurements on almost any variable, you'd find that the values are not all the same. In fact, they tend to distribute along a range of values, and that distribution looks often a lot like a vaguely bell-shaped curve, and this is especially the case as the sample size increases. And I think you can have a kind of an intuitive sense of this if you just imagine measuring almost anything. It could be IQ, some feature of personality, it could be shoe size, it could be height. And if you had only a very small number of people, 5 or 10, you wouldn't necessarily expect those values to distribute in something that looks like a kind of a symmetrical bell-shaped curve. But if you had those same measures for 500 people or 5,000 people, you'd very likely have a relatively few number of people who have very high values on whatever it is you're measuring, probably about as many who have very low values, and then most of the people kind of piling up towards the middle. And for as much of psychology, we tend to assume that the things that we are studying are distributed in a normal fashion in the population. So we make the assumption that things like various personality traits, intellectual abilities, aptitudes, and the like are normally distributed in the population. This tends to be the case. It tends to be empirically observed, as I've noted before. But it's not a law of nature. There are some data that are not normally distributed in the population. But even in these cases, they often tend to look pretty close. So as an example, that IQ is not, strictly speaking, normally distributed. There is a negative skew to the distribution owing mostly to the fact that there are people who have relatively low IQ because of birth defects or in some cases traumatic head injuries. But even there we see a distribution that is close to normally distributed, and at least with IQ the way we typically measure it, centered over about 100 with a standard deviation of about 15. Now, this assumption that things are normally distributed in the population is a useful one to make because a normal distribution is mathematically defined, and so we know the frequencies of values that we should find at different points on that distribution. And as you know from other classes, I'm sure, this assumption about normal distributions is a cornerstone of a lot of the statistics that we do. And although I'm not going to talk a great deal more in this lecture about statistics, it is often useful to assume that the thing you're studying is normally distributed in the population. I mentioned before that the normal distribution is mathematically defined, and you've certainly seen images like this in our textbook or in other textbooks. We know in a normally distributed set of data that approximately 68% of the data lie within plus and minus 1 standard deviation of the mean, 95% roughly within 2 standard deviations, and almost all of it within 3 standard deviations above and below the mean. Another opportunity to practice: take a look at your data and try to decide whether your data are normally distributed. How could you decide whether or not the data are normally distributed? So to tie this back to some points that I've made earlier, we could imagine looking at a set of data from a sample drawn from a population and examining it to see if the data is skewed. Now, this examination is interesting to us because it may, for instance, highlight the presence of outliers. We may be curious to see a non-normal distribution of data in our sample, and if we do, we might be a little bit concerned about how interpretable some of our measures of central tendency for that sample data are. For instance, if the data is very skewed, we might not want to focus on the mean as an indicator of the center of the distribution. We might also be curious or concerned if the thing we're measuring, we assume, is normally distributed in the population. So again, you could imagine developing some sort of a measure for, let's say, some aspect of personality that you assume is normally distributed in the population, and then you gather a sample from that population and you look at the sample distribution and see that there is some skew, there's some non-normality to it. If the data in the sample distribution isn't normally distributed, what might that mean? Well, it could mean there's something, quote, wrong, unquote, with the population. Maybe, in fact, the thing you're studying in the population isn't normally distributed. I used the example a couple times in this lecture of an anxiety measure that I'm supposedly developing. It's reasonable to suspect that anxiety is not normally distributed in the population. It's probably has quite a positive skew, meaning most people have little or no anxiety, hopefully, but there are some people who have quite a lot of anxiety. So if I was developing that questionnaire, I gathered my sample of data, I observed that my sample of data wasn't normally distributed and was in fact skewed. I might look at the outliers that are kind of part of that skew and scrutinize them. Maybe there's something wrong with those individual cases or something peculiar about them. But I might also wonder if there's something, in a sense, wrong with the population. That is, that it's not normally distributed. And of course, I'm putting wrong in quotes here because we don't necessarily have to assume that things are normally distributed in the population. They often are, but they don't have to be. if the sample data isn't normally distributed, it also could mean there's something wrong with the sample data. And that's something that we probably should be concerned about, or at least investigate. And there are at least a couple sources of non-normal distribution in sample data that are of particular concern to people who are developing new measures, to psychometricians. One is problems in item selection, which we might otherwise call issues of measurement error or measurement bias, and the other are issues of sample selection, which we otherwise might call sampling error or sampling bias. And I've actually, of course, already talked about that a little bit. So let's focus on item selection first. Imagine you've gathered a sample of data from a population. You've observed that it's not normally distributed, that in fact there is some skew to it. And let's imagine that you're still fairly confident that in the population that thing ought to be normally distributed. Thus, you're kind of thinking more that the problem's with your sample than with your population, so to speak. Anyway, what could this mean? Well, it could be the case that this positive skew comes from a problem with item selection. So for instance, positive skew could happen if there are too many difficult items on the test, assuming that this is a test of ability or aptitude or achievement, where there are essentially right and wrong answers to each item. So if there are too many hard items, most people's scores tend to pile up on the low end. Very few people maybe get high scores because they're really quite bright or quite able or quite whatever, but most people pile up on the low end. Like, the example that probably we've all experienced of taking a class where a particular test is just too hard and everyone in the class fails, or at least most people do. And it could be the case that a similar sort of positive skew could occur if there are just too many items that few people endorse, if this is a test of emotion or temperament or personality or opinion or something else where there aren't, of course, right or wrong answers for each item. But it's just the case that there are a lot of items on the test that most people don't agree with or don't identify with. So again, most people's scores pile up on the very low end, and a very few people are on kind of the high end because they are unusually high in whatever that trait or that quality is. Now, negative skew is, of course, just the opposite situation. If we're talking about a test of ability or aptitude or achievement, there are just too many easy items. Everyone aces the test, and a few people, sadly, maybe still fail it, and thus there's a skew off in the negative direction. Or if this is a test of emotions or temperament or personality or opinion or whatever else, there are too many items on the test that everyone endorses and everyone agrees with, and only a few people tend to disagree with a lot of them, thus producing a negative skew. So what's the point of all this? Well, it could just be the case that your skewed sample data has to do with kind of odd or unfortunate item selection. And if you were doing test development, if your goal was to develop a robust and a useful, valid test, you might scrutinize that distribution and think, maybe there's a problem with item selection here. Could also be the problem, or it could also be that there's a problem with sample selection, that your sample doesn't really represent the population that you think it represents. Maybe there are sort of disproportions of subgroups or subpopulations within your sample that you're not quite aware of. For instance, in the example I used earlier, you are recruiting from a sample of people in the 18 to 25-year-old range. Your goal is to generalize to that population, but whether you realize it or not, your sample overrepresents people who are in college or university as compared to people who are not. And that could lead to odd, non-normal distributions of responses to your test questions. It could be the case that your sample doesn't come from just one population, but maybe combines populations that ought to be distinct. You were sloppy or unlucky in your recruitment of participants for your test development study, and you accidentally included people who really aren't part of the population you're surveying. We could get a bit technical and say, well, if it's positive skew, maybe you have too many low performers or bad performers. If there's negative skew, too many high performers or good performers. But the point, or the basic idea, is that a non-normal distribution of sample data might be the result of problems with item selection, or it could also be the result of problems with sample selection or sampling error, kind of like I described a little bit earlier in this lecture. What can you do about this? Well, a lot, hopefully. In the case of item selection problems, you can re-examine your items, try and get a better balance of easy and hard items, or uncommon and common items, depending on the type of test you're developing or type of measure you're developing. In the case of sample selection problems, you could examine subgroups. You could see if you can discern within your sample meaningful groups and then compare them in terms of their average levels of test performance, kind of taking an ANOVA approach, saying, well, what if we compare men and women, or college and non-college educated, or find subgroups and test to see if they are meaningfully different on whatever that thing is you're measuring. Another similar, although kind of more regression flavored approach would be to look for individual difference variables that predict the score on whatever it is you're testing. So if you're developing some measure of anxiety, let's say, are there individual difference variables like gender, age, other psychopathology, drug alcohol use, etc., which are predictive of your score on your anxiety measure? If the answer is yes, then maybe you have to be careful not to to have a sample which reflects a broad range of values on those predictive variables, those predictor variables. Otherwise, you might get into a situation where your measure is overly representing people who are high in those individual differences. And of course, another approach, or related approach, is just to gather a new and hopefully bigger sample on the expectation that larger samples tend to be more representative of their populations and tend to look more normally distributed anyway. What else can you do? Well, a final thing that isn't necessarily independent of those other approaches or ideas that I just mentioned is to try to transform your data. This often happens in situations where there are distributions of data which are not normally distributed, but which we have good reason to think shouldn't be normally distributed. Things like levels of psychopathology, levels of drug or alcohol use, reaction times on psychophysics type tests. There are all sorts of things which just aren't normally distributed in sample data, which we wouldn't necessarily expect to be normally distributed in population data, but we still might nonetheless want to alter the way the scaling of those scores works to make them appear somewhat more normal in shape, and thus a little bit easier to interpret. And I'll talk about that a little bit later on in this lecture, actually in just a couple more slides. But suffice it to say that that's something that you could do, or you might do in addition to some of the other steps, to deal with odd, skewed, non-normal distributions of sample data. Important points here, and I'm kind of repeating myself really, is that test scores need to be put into a context. This context for norm reference tests often is based on the idea of the relationship between the individual score and the sample and the population distribution that that person is a part of. We're often estimating that population distribution from our sample distribution. And it's important to evaluate sample distributions to understand their shape, their center, their dispersion. This is especially true, of course, when you're developing a new measure. That's why, of course, I've repeatedly used this example of, let's imagine I'm developing a new anxiety measure. But it's also important even if you're using an existing measure. If you're administering the Beck Depression Inventory or the Wechsler Adult Intelligence Scale, it's worth cracking open that test manual and reading through the technical information on the standardization sample and getting a sense of what the distribution of values is for any of the particular variables that you're measuring with that instrument. What's the distribution of values for the Beck Depression Inventory in the standardization sample for that instrument? It's something to kind of educate yourself about, so you better understand how to use the instrument, how to use the test. Okay, in the last section of this lecture, I'm going to talk a little bit about raw score transformations. These are things that we do sometimes when dealing with non-normally distributed sample data, and sometimes we just do it anyway to help make raw scores from tests easier to describe, to explain, or to compare to other test scores. I should say many of these will be familiar to you either from other classes or just from your own experience of education. One of them, of course, are percentiles. Percentiles just represent the percentage of cases in the sample distribution that fall below a particular score, and higher percentiles indicate higher scores. So, we might know this from our own education. If you score in the 99th percentile on a test, you know that means 99% of the people who took that test fell below your score, and you probably feel proud of yourself for that. It's also worth reminding ourselves that the 50th percentile, or sometimes called p subscript 50, indicates the median. That's the cut that separates the upper half and the lower half of the distribution. Now, percentiles are nice. They have some advantages. There are some reasons why we sometimes convert raw scores to percentiles. One is they're fairly easy to understand. I think most people, even people who are not that familiar with psychological testing, can appreciate the idea of a score which is above 50% of the other scores, or above 75%, or above 99% of other scores. And that ease of communication is important. And of course, implicit or built into percentiles is the idea of ranking. That is to say, if we wanted to rank people by their scores, where does one particular individual stand with respect to all the other folks in the distribution? Now, some disadvantages, or really one big disadvantage here, is that it's sometimes not recognized that they actually distort the distribution of scores in such a way as to compress extreme values. And this is something you're kind of familiar with if you've taken large classes as an undergraduate. I certainly can remember taking large chemistry classes at university and being frustrated by the differences between percentiles at different points in the distribution. So for instance, the difference between, let's say, the 50th and the 59th percentile is relatively small as compared to the difference between the 90th and the 99th percentile. And I think to someone who's not well trained in testing, or someone who's a little bit unfamiliar with psychometrics, or just percentiles more specifically, it's easy to overlook that and think, oh, well, someone, I scored 10 percentile points above you, and this person scored 10 percentile points above me. Those are equal differences, right? Not necessarily. In fact, almost certainly not the case. And that can sometimes be a little bit obscured if we're not careful. Another problem with percentiles is they're sometimes mistakenly thought of as percentage of items correct or items endorsed. So if someone says, if you say of someone, oh, she scored in the 99th percentile, to an untrained listener that might sound like she got 99% of the questions right, assuming it's a test of aptitude or ability or achievement or so on. And that's not true. All percentiles are doing are representing a position of one case relative to a distribution of other cases. Related to percentiles are percentile ranks. These are just ranks based on percentiles. So you take percentiles and you treat them like a set of 100 cases. The lowest score is given a percentile rank of 1. The highest score is given a percentile rank of 100. And so you can, for each person's score, assign a percentile rank based on their percentile. Some people do this. It's a way of communicating similar information to percentiles. It just, in a sense, gets away from using the percentage symbol in the coding or in the presentation of the information. And it's also worth noting this is roughly the opposite of the way we normally think of rank. 1 being first place. In the case of percentile ranking, 1 is last place if we're talking about an order of achievement or ability or so on. But it's not fundamentally all that different. Percentile ranks in percentiles. Another thing we can do with raw scores is transform them into standard scores. And this is the familiar z-score transformation that I think we all remember, hopefully, from statistics and research methods classes. You take a person's individual score, you subtract the mean, you divide by the standard deviation, and you've got a z-score for that person. The advantage of the z-score is, unlike percentiles, it doesn't distort the distribution of scores. The differences between different z-scores are consistent. They are not inconsistent, as is the case in percentiles. A disadvantage is it doesn't distort the distribution of scores, and depending on the nature of the data you're working with, you might enjoy, or you might want to compress or distort a distribution to, for instance, make it more normal. And if this seems like a bit of an obscure point, I'm only really making it because I think sometimes people mistakenly think that converting raw scores to standard scores or z-scores somehow magically corrects for problems of non-normal sample distribution. Like, oh, we have this really skewed distribution, but don't worry, we converted everything to z-scores. Well, there may be good reasons to convert things to z-scores, but changing the shape of the distribution isn't one of them because it doesn't do that. More advantages of z-scores, well, as you probably know from other classes, they have mathematically useful properties. Particularly the mean of a group of z-scores will be 0, the standard deviation of 1 will be 1, which makes it relatively easy to interpret a z-score. So if I tell you this person has a score of 72 on my test, you don't know much about where that person stands relative to anyone else in the distribution of scores for that test. But if I tell you this person has a z-score of 2, you know that she has a score that's 2 standard deviations above the mean, assuming that the data is normally distributed. This is really useful for all sorts of reasons because it can help, among others, it can help us to detect outliers or extreme cases. You know, it should be very rare that we see cases with standard scores of absolute value 2 or 3 or higher in a distribution of data. Not impossible, but just pretty rare. If we had a distribution of sample data where there were lots of values, standardized values that were in the range of 2 or 3 or 4, we might be concerned that there's a really skewed distribution here, which again might be okay depending on what it is we're studying, but it might not if we're expecting that what we're studying is normally distributed. You know, another advantage that you often hear about z-scores is that it's useful for comparing for comparisons between scales. So let's imagine I administer a test of ability to a particular client, and she scores 2 standard deviations above the mean, so her IQ or her mental ability is quite high. It's unusually high, at least as compared to the standardization sample. But then I administer a test of achievement, that is kind of the knowledge she's gained from schooling, and that's 1 standard deviation below the mean. Well, that's odd. You know, I might think this person has a lot of ability, but they're not gaining much from their schooling. Maybe there's a learning disability or some sort of other reason that explains this apparent discrepancy between their ability and their achievement. That you know, sort of diagnostic inference I'm making depends in part on my ability to compare across 2 different tests, which may have in their raw scores very different metrics, but if I convert those raw scores to standard scores, they can be more easily compared to one another. An important caution or caveat here is that this only works if the distributions of the scores for my 2 tests are similar. If they're not, then those comparisons aren't as easy to make. So let's imagine here I have 2 tests. One, as you can see in the you know, the lower portion of the screen, is fairly normally distributed. I guess it's a little bit platykurtic maybe, but the one in the upper portion of the screen is not normally distributed, or at least if it is, it's rather skewed. Now the position, if someone scores 1 standard deviation above the mean on both of these scores, they're not at the same position on each test relative to the other cases. You know, someone on the test in the topmost portion of the screen is at the 92nd percentile if they're 1 standard deviation above the mean, but in the second test they're at the 84th percentile. So comparisons, you know, is someone, how high above the mean is someone on this test? Well, how high are they above the mean on this other test? Those comparisons can be made by using standard scores, z-scores, if the distributions for those tests are similar. Ideally, if they're both normally distributed, that's the best situation, but at least if the distributions are similar. If they're non-similar, then those comparisons are less useful or less valid to make. So a little bit more practice, use my fictitious data set and do some basic transformations, find percentiles, percentile ranks, and make some standard scores. Okay, assuming you've done that, let's move on. There are some problems with standard scores, z-scores. Not big problems, I would argue, but there's some things that make them a little bit confusing. One, they have both positive and negative signs. So positive signs are values that are above the mean, negative signs values below the mean. Those can be confusing to people who are unfamiliar with standard scores, especially people maybe who aren't psychologists or even aren't scientists. They see the negative and it scares them, like, oh, is someone losing ability, or are they going down, or is negative somehow bad just because of the associations we have with that numerical concept. The other thing that can be confusing about z-scores, standard scores, is they have decimal fractions. So if someone's z-score is 1.5, it's not, people might be tempted to round that up or round that down, or they might not know what to do with that. Again, this can be especially confusing to non-psychologists or non-scientists. As a result of this, or in response to this, there are a variety of different standardized scores that you can compute. Standardized scores are just transformations which are applied to standard scores to make them more interpretable or easier to interpret. And really the best example of this is the t-score. Now you're probably familiar with t-scores from other classes. You've probably seen them before, but just as a reminder, a t-score is just a standardized version of a standard score, or it's a z-score that's been changed such that the mean is no longer 0 but rather 50, and the standard deviation is no longer 1 but rather 10. How you get from a z-score to a t-score is pretty simple. You just multiply by 10 and add 50, and there you go. And t-scores, again, you're probably familiar with them. They're common in psychological tests. So for instance, the MMPI uses t-scores, a lot of other tests do. And as a rule of thumb, we just expect that most of the data are going to fall between about 20 and 80 in a set of t-scores, or maybe even more like 30 and 70, reflecting sort of 2 or 3 standard deviations above or below the mean, with the mean as 50. And if you're having a hard time picturing this, just see here in the top of the image here a standard, a normal curve, a normal distribution. If you go down to the first row, you can see the percentiles for the different points in that normal distribution. Notice that the spacing between those values of percentiles is not constant. I kind of talked about that earlier. If you go down another level, you can see z-scores with a mean of 0, standard deviation of 1, pretty straightforward, and you can see t-scores underneath that. You can also see a bunch of other standardized scores, some of which we'll talk about. So for instance, the way most IQ scores, like on the Wechsler or on the Stanford-Binet tests work, is they're set up such that the mean is 100 and the standard deviation is 15. And for some of the subtests, or I think really all the subtests on the Wechsler tests, it's just set up such that the mean is 10 and the standard deviation is 3. Those are just conventions that are done to make those scores more interpretable to the people who commonly use them. So t-scores, advantages? Well, they're easy to interpret. They don't distort the distribution of scores like a percentile or percentile ranking approach would work. Again, disadvantages would be, well, they don't distort the distribution of scores, which mean that they don't correct for problems of skew. And again, if this seems like a bit of an obscure point, this is just me again indicating that there's nothing really magical about z-scores or t-scores with respect to changing distributions of sample data. Occasionally you'll hear people say things like, well, we had this skewed data, but we converted everything to t-scores, so problem solved. Well, no, not problem solved. More practice, try converting your standardized scores to t-scores. Not very hard to do. You can use that little formula that I had a few slides back. Okay, so a couple times now I've mentioned that z-scores and t-scores, they don't change skew. Percentile scoring does. Is that a problem? Is there not a problem? what do you do if you have skewed sample data, assuming you want to get rid of that skew? Now, to be clear, there may be plenty of times when you're measuring something which you don't expect to have a normal distribution in either the sample that you gather or indeed the population. You might be measuring some aspect of personality, some aspect of psychopathology, like anxiety, and you expect that most people have little or none of it, and some people have a lot. Or you might be measuring reaction time and expect that most people will be relatively fast, that is low reaction time, some people will be relatively slow. A lot of times there'll be variables that we study that have positive skew, but assuming that this is the case for you and assuming you want to do something about that skew to reduce it, what can you do? So you may have encountered in other classes the idea of nonlinear transformations for data, things like log or square root or reciprocal transformations. These are often done to reduce skew of data. So you could imagine you have a set of data, these are scores from a test that you've administered, and let's say the distribution is rather positively skewed, so you decide to square root each person's score. If you did that, the people with really, really high scores get their scores reduced quite a bit, and quite a bit more than do people who have smaller or lower scores. That tends to pull in that positive skew, that tail that's sort of drifting off in the positive direction. Log transformations, reciprocal transformations have some similar effects. These are sometimes called normalizing approaches because they tend to make skewed distributions look a little bit more like normal distributions. Another example of this idea is so-called normalized standard scores. These are done if you find the percentile rank of each score. Again, that has a kind of a compressing effect. It tends to reduce skew in both directions. And then using those percentile ranked scores, you compute standard scores. We begin with a non-normal distribution and we end up with a distribution that looks more normal. We've reduced skew in both directions. It can reduce both positive skew and negative skew. Advantages, like I already said, it can reduce or even eliminate skew. Assuming that that's what you want, it's a good thing. Disadvantages, well, again, this is sort of, is it an advantage, is it a disadvantage? It really depends on your perspective. This distortion of values, this sort of pulling in of extreme values, necessarily distorts the distribution, and in really extreme cases of this, it can even shift values across the mean. That would be somewhat unlikely to happen, but it certainly could happen in a really extreme case of normalizing a very skewed distribution. In extreme cases, it can make a scale hard to interpret because you're looking at a score which is no longer a raw score. It's not even a percentile rank, but it's now a standardized percentile rank, and for most people that can be a little bit tricky to think about. And like I said before, it may just be the case that the population that you're looking at, I should say the distribution of values in the population that you're studying might itself not be normally distributed. So the whole idea of trying to normalize a sample of data, it could make sense, but it might not make sense. And it really depends sort of on what you're studying and what your perspective is. If all that sounds again, a bit obscure, a bit vague, let's bring it back to an important point or two. First, this is that raw scores are uninterpretable usually, and as I've said a couple times now in this lecture, they need to be put into context. For instance, comparing them to norms drawn from a representative sample from a population where we have good reason to assume a particular shape or distribution in that population. Sometimes we need to transform our raw scores, for instance, into standardized scores or t-scores. Often this is to make them easier to read or communicate or think about. Okay, so it's been a fairly long lecture. Thank you for sticking with me. In the next lecture, I'll talk a little bit about standardizing a test, that is developing norms. I've talked about how most tests that we look at have these published norms, and I'll try and talk briefly about where these come from. And then I'll start to talk about things like reliability, this important psychometric quality that we often try to assess in different ways. There are different ways of thinking about reliability of an instrument, and they're worth considering. In the way to considering them, I'll talk about classical test theory, our first major psychometric theory. I'll also talk about measurement error, which I've mentioned already, and I'll get into a little bit more. Okay, as I always say, thanks for your attention. That's all for this lecture. I really do appreciate it. If you have questions, of course, try to ask me. If you don't, then I will see you in the next lecture. All right, bye-bye.